Two galaxies clusters just crashed in the deepest void. This is the Bullet Cluster, the most violent collision we have ever seen, and it revealed a ghost. Most of the mass in that cosmic wreck was completely invisible, sailing right through the chaos as if it wasn't even there. That ghost is dark matter, the universe's greatest and most elusive mystery. For years, that one image was our best proof. But what if I told you it was just the beginning? By the end of this, you will understand how an entire arsenal of cosmic crashes is locking in the reality of the dark universe, proving it beyond any reasonable doubt. Astronomers are now finding bullet cluster analogues, other titanic collisions that repeat the same impossible story. They show dark matter lagging behind, racing ahead, or pooling in strange, dark cores. How can something we cannot see define everything we can? And what do these cosmic train wrecks tell us about the fate of all existence? What does it feel like to finally map the invisible? Think of the universe's largest objects having a car crash in slow motion. That is the Bullet Cluster, officially known as 1E0657-56. It is not one single thing, but two entire galaxy clusters, each containing hundreds of galaxies that plowed into one another at millions of miles per hour. For scale, a single galaxy like our Milky Way is already an island of hundreds of billions of stars. This was a collision of two sprawling metropolises of such islands. Now, in any collision, you expect the most visible stuff to get stuck in the middle, like two clouds of smoke merging. And that is exactly what happened with the hot gas between the galaxies. This superheated plasma, which glows brightly in X-rays, slammed together and pooled at the center of the wreck. Astronomers call this glowing, distorted cloud the bullet. But the galaxies themselves, those pinpricks of starlight, did something utterly bizarre. They simply kept going, like two swarms of bees that passed through each other almost untouched. The galaxies sailed right through the collision because space between stars is so vast. So you had the visible galaxies on one side and the glowing gas cloud lagging behind on the other. But here is where the ghost appears. When scientists used a cosmic magnifying glass called gravitational lensing to map where the actual mass was, the result was impossible. The true heavyweight of the crash was not with the bright, hot gas. It was not even spread evenly. The map revealed a huge concentration of mass perfectly aligned with the galaxies that had sailed through. It was as if you watched two cars collide, saw the glass and metal scatter, but then a footprint in the mud showed an invisible driver had stepped out and walked away unscathed. The dark matter, which does not glow or collide, had simply ghosted through the entire cataclysm, leaving the normal matter behind in a tangled mess. This was the first time we had a direct, observational map separating the dark universe from the light one. It was not just a theory anymore, it was a fingerprint at a cosmic crime scene. This separation is the key to everything. Think of it as the universe's most perfect natural experiment, a laboratory built on a scale of millions of light years. To understand why, we need to look at the fundamental difference between the stuff we are made of and the dark ghost that holds it all together. Normal matter, the atoms in your body and the stars in the sky, is social. It interacts. Protons and electrons carry electric charge, which means they constantly talk to each other through electromagnetic forces. They push, they pull, they crash, they create friction. Now picture that superheated gas cloud between the galaxies. It is a seething sea of charged particles. When two clusters collide, these two seas of gas slam into each other. It is a cosmic traffic jam. The particles get tangled, they exchange energy, they slow each other down dramatically. That is why the hot gas gets stuck in the middle, glowing like a bruised and battered aftermath. But dark matter is the ultimate loner. According to our best model, called cold dark matter, it does not carry any electric charge. It feels no electromagnetic force at all. It is utterly silent in that conversation. The only way it interacts with anything, even itself, is through the whisper of gravity. So when two clouds of dark matter pass through each other during a cluster collision, there is no friction, no traffic jam, no slowing down. The dark matter particles, if they even notice each other, just sail right on through like phantoms in the night. This creates a clean, physical separation. The sticky, social normal matter piles up in the center. The antisocial, non-interacting dark matter keeps going with the galaxies. And here is the genius part of this cosmic experiment. We have two completely independent ways to map the aftermath. With X-ray telescopes, we can see exactly where the normal matter gas ended up, that bright, tangled cloud. Then, using gravitational lensing, we can map where the actual mass, the true gravitational anchor of the system, ended up. When those two maps do not line up, when the mass is somewhere else entirely, we have directly detected the presence and the behavior of something invisible. This is not a theory on a chalkboard. It is a prediction of the cold dark matter model playing out in real time, in the most violent arenas the cosmos has to offer. The bullet cluster was not just a lucky snapshot. It was a revelation of a fundamental rule of the universe written in the aftermath of a collision. But one cosmic crash was not enough for science. A single fingerprint can be a fluke, a trick of the light. To prove a ghost is real, you need to see it again. And that is exactly what the Hubble Space Telescope and the Chandra X-ray Observatory found, staring at a patch of sky with the catalog number MAX J0025.4-1222. Astronomers call it the baby bullet. This was the first major analog, a near-perfect replica of the original bullet cluster, but seen from a different cosmic perspective. While the original collision happened more or less across our line of sight, the baby bullet presented itself almost face-on, like looking down at two cars that have just T-boned each other. This new angle was crucial. It allowed scientists to measure the separation between the dark matter and the normal gas with even greater precision, as if they had moved to a better seat to watch the experiment unfold. The data told the same impossible story. The Chandra telescope saw the glowing aftermath of the hot gas, pooled and shocked in the center of the collision. But Hubble's keen eye, using gravitational lensing to map the mass, revealed the true anchors of the system, two huge clumps of dark matter that had sailed right through the chaos, flanking the gas on either side. The separation was clean, undeniable, and a perfect mirror of the original finding. This was not a fluke. This was a repeatable result. The universe was running the same experiment twice under slightly different conditions and getting the same answer. For theories that try to explain away dark matter by modifying the laws of gravity, like modified Newtonian dynamics or MND, this was a devastating blow. Those theories struggle to explain why, if gravity just works differently, the effect would so cleanly separate from the visible matter in not one, but two independent cosmic crashes. The baby bullet was proof that the ghost had a predictable behavior. It was not an anomaly, it was a pattern. And if there is a pattern, there is a reality waiting to be understood. The pattern grew stronger with a second, even more telling witness. Meet the Musket Ball cluster. Its official name is a string of letters and numbers, DLCLJ0916.2 plus 2951, but astronomers gave it a more evocative nickname for a reason. If the original was a high-velocity cosmic bullet, this is the slower, older musket ball, a relic from a collision that began nearly 5 billion years ago. That timeline is crucial. It means this crash happened when our sun was just a newborn star in a dusty nursery. By studying it, we are not looking at a fresh wreck, but one that has been sitting in the cosmic junkyard for ages. And what we see there locks the case shut. The separation between dark matter and normal matter is not just a momentary flash in the pan, it persists. Billions of years after the initial impact, the dark matter is still cleanly separated from the pile of hot, glowing gas. Think of it like finding an ancient battlefield. The original bullet cluster showed us the moment of impact with debris still flying. The musket ball shows us the same battlefield but centuries later. If the dark matter ghost had any tendency to slow down, to eventually mix back in with normal matter over cosmic time, we would see the maps blurring together here. They do not. The ghost is still exactly where it sailed off to, holding its shape, maintaining its distance. This proves the collisionless nature of dark matter is not a temporary quirk, it is a fundamental and stable property. It does not interact, period, not in the heat of the moment and not over the slow march of eons. Each of these analogues is like a different frame in a cosmic film, and together they show us a consistent story of an invisible actor that plays by its own silent rules. Yet the story of cosmic collisions is not always one of clean separation. For every elegant bullet, there is a messy, chaotic train wreck. This brings us to the third and most controversial witness, Abell 520, often called the train wreck cluster. Here, the universe seemed to break its own rules. Instead of a simple two-cluster collision, Abell 520 is a violent, ongoing pile-up involving multiple clusters. It is a cosmic freeway accident with debris scattered everywhere. The initial maps of this system, using gravitational lensing, delivered a shocking result. Scientists found a massive, dense concentration of dark matter, a dark core, sitting right in the middle of the collision. But this dark core was not aligned with a swarm of galaxies. It was in a region almost devoid of bright galaxies, which had mostly sailed onward. This was the complete opposite of the bullet cluster. Instead of dark matter ghosting ahead with the galaxies, it appeared to have gotten stuck in the middle, like it was lagging behind or even attracted to itself. This single observation sent shockwaves through cosmology. Could dark matter actually interact with itself? Could there be a dark force, a kind of shadow version of the forces that govern our world, that cause dark matter particles to stick together or slow each other down? The idea of self-interacting dark matter became a serious contender, a potential crack in the perfect non-interacting model. For a while, Abell 520 was the great exception, the cosmic outlier that threatened to rewrite the dark matter rulebook. It was a powerful reminder that nature loves to throw us curveballs, and that our maps of the invisible are only as good as our tools and our interpretations. The controversy raged for years until newer, more powerful telescopes took a closer look. Higher resolution data from observatories like the Hubble Space Telescope began to untangle the mess. The picture that emerged was more complex but ultimately more consistent. That puzzling dark core was not a simple, isolated blob of self-interacting ghost matter. Instead, it appeared to be associated with a faint sea of stars that had been stripped from their home galaxies during the violent collision, along with a significant amount of hot, dim gas. This suggested the dark matter might not be entirely alone in that region after all. The current interpretation is that Abell 520 represents an earlier, messier stage in the collision process, where the debris field is so complex that our maps are still untangling the signal from the noise. Rather than disproving the standard model, this train wreck cluster became its most rigorous stress test. It showed that by studying these extreme environments, we are not just looking for confirmations, we are probing the very limits of our understanding. Each analogue, whether it shows a clean separation or a confusing pile-up, is a different question posed to the dark universe, and the universe in its infinite complexity is answering. The universe was not done building its case. Far beyond the local cosmic wreckage, another collision was unfolding on a scale so vast it defied belief. Astronomers named it El Gordo, Spanish for the Fat One, and it is officially catalogued as ACT-CLJ0102-4915. This is not merely another cluster crash. It is the most massive colliding cluster we have ever seen in the distant universe, a titan caught in the act of a catastrophic merger. Its light has traveled for over 7 billion years to reach us. We are seeing it as it was when the cosmos was only about half its current age, a much younger and more violent place. To find something this enormous so early in cosmic history was at first a profound puzzle. According to our standard models of how structure forms in the universe, it takes time for gravity to pull matter together into such behemoths. Finding El Gordo was like discovering a skyscraper in the middle of an ancient, undeveloped plain. It simply should not have been there yet. But when scientists used the Hubble Space Telescope and ground-based observatories to map its mass through gravitational lensing, the dark matter ghost provided the explanation. The lensing map revealed the now familiar signature, a clear separation between the seething clouds of hot normal gas and the invisible gravitational anchors of dark matter. This proved that the titanic mass of El Gordo was real, and more importantly, it showed how such a monster could assemble so quickly. Dark matter acts as the cosmic scaffolding. Its gravity creates the initial wells that normal matter later falls into. The existence of El Gordo, with its dark matter clearly in command, told us that this scaffolding was already incredibly robust and clumpy in the early universe. The dark matter had already woven a web strong enough to support the weight of a cosmic giant. This distant collision became a critical test for our entire cosmological model. It asked the question, can our theories of dark matter and cosmic evolution explain the formation of the largest structures we see, even in the universe's youth? The answer, written in the lensed light of El Gordo, was a resounding yes. The ghost was not just present, it was already hard at work, building the architecture of the cosmos on a scale we are only beginning to comprehend. The ghost's signature grows clearer with every cosmic wreck we examine, but to truly understand its nature, we must visit the most chaotic aftermath of all, a place astronomers call the Pandora Cluster. Its official name is Able 2744, but that clinical label does no justice to the scene. This is not a clean collision between two giants. This is the tangled, shredded wreckage of at least 4 separate galaxy clusters that have been smashing together in a series of mergers over hundreds of millions of years. It is a cosmic demolition derby, a pile-up of epic proportions where the debris field tells a story of multiple impacts. Untangling that history required a forensic investigation on a galactic scale. Astronomers became cosmic detectives, bringing every tool at their disposal to the scene. The Chandra X-ray Observatory mapped the searing hot gas which glowed in tangled, twisted ribbons. The Hubble Space Telescope and the Very Large Telescope captured the faint light of the galaxies themselves, strewn about like survivors wandering from the crash. And then, using the subtle warping of space-time through gravitational lensing, they painstakingly charted the true gravitational anchors, the map of mass itself. What they found was a masterpiece of separation. In this incredible mess, the 3 main components of the universe, galaxies, hot gas, and dark matter, had been violently pulled apart from one another. One huge clump of dark matter was found with no galaxies and very little hot gas. A separate, dense knot of hot gas was discovered, blazing in X-rays but with almost no dark matter or galaxies to keep it company. And a collection of galaxies was identified, sailing through space largely stripped of both their dark matter halos and their gaseous atmospheres. This was the ultimate stress test. The Pandora cluster proved that the ghostly behavior of dark matter is not a neat party trick that only works in simple, head-on collisions. Even in the most complex, multi-stage pile-up imaginable, the fundamental rule holds true. Dark matter, because it does not interact with light or with itself in any significant way, gets separated. It is filtered out from the normal matter through the sheer violence of these events. Pandora's box, once opened, did not release chaos but clarity. It showed that by studying even the most mangled wreckage, we can isolate the invisible component, measure its properties, and confirm that it is a real, physical substance that behaves according to predictable laws. This complex cluster became a rich testbed, a cosmic laboratory where we could observe the ghost in multiple states, separated, isolated, and defining the gravitational landscape of pure chaos. The ghost leaves no light, but it always bends space. To see it, we have to become detectives of distortion, reading the subtle warps in the very fabric of reality. This is the technological triumph behind every dark matter map. It begins with a cosmic magnifying glass built by gravity itself, a phenomenon called gravitational lensing. When the immense mass of a galaxy cluster sits between us and a more distant galaxy, its gravity acts like a lens in a telescope, bending and magnifying the background light. Sometimes the effect is dramatic, creating multiple images of the same distant galaxy, or stretching it into long, luminous arcs around the cluster's center. Astronomers call this strong lensing, and it's like seeing the ghost's hand directly twisting the light. But more often, the effect is incredibly subtle, a slight, coherent stretching of thousands of faint background galaxies, making them appear just a bit more elliptical than they truly are. This is weak lensing, a statistical whisper across the sky. To measure it, you need a telescope with exquisitely sharp vision, capable of seeing the shapes of galaxies billions of light years away. That is the domain of the Hubble Space Telescope. For decades, Hubble has stared at these clusters not to see the bright foreground galaxies, but to catalog the faint, distorted shapes of the background universe. It collects millions of these tiny, warped fingerprints, but raw images are just the beginning. This is where the computational magic happens. Scientists run these mountains of data through sophisticated pipelines, algorithms that statistically subtract the natural, random orientations of galaxies to reveal the coherent pattern of distortion imprinted by the invisible mass. What starts as a field of faint smudges is transformed, line by statistical line, into a stunning topographic map of gravity itself, often rendered in cool, ethereal blues and purples to show where the dark matter pools. But a gravity map alone is not proof of separation. You need to compare it to a map of the normal matter. That is where other eyes come in. Space telescopes like Chandra and XMM Newton see the universe in X-rays, a form of high-energy light invisible to our eyes. The multimillion-degree gas trapped between the galaxies glows fiercely in this band. These observatories paint the scene in fiery reds and oranges, revealing exactly where the normal, collisional matter ended up after the crash. When you overlay the two maps, the blue haze of the gravitational mass and the red cloud of hot gas, the truth becomes visually undeniable. They are in different places. Ground-based observatories add the final piece, using optical and infrared cameras to pinpoint the locations of the actual galaxies, the pinpoints of starlight that sailed through. This multi-messenger approach, combining the sharp eyes of Hubble, the fiery vision of Chandra, and the wide gaze of ground telescopes, is how we assemble a complete forensic picture of a cosmic crime scene. We are not just looking at the universe, we are listening to it in different wavelengths, translating its hidden signals into a story we can see and understand. Each color in these composite images is a different language, and together they tell the same impossible tale of a ghost walking through walls. These cosmic pile-ups are spectacular, but the ghost's signature appears on smaller scales too. To find it, we shift our gaze from titanic clusters down to individual galaxies crashing in slow motion. This is a more intimate but no less revealing kind of collision. When two galaxies like our Milky Way spiral toward each other over hundreds of millions of years, their dance is choreographed by the invisible. The most famous example is a pair known as the Mice galaxies, officially named NGC 4676. From our distant vantage point, they look like two glowing rodents with long, streaming tails stretching across space. Those spectacular tails are tidal forces at work, vast rivers of stars and gas ripped loose by the immense gravitational pull of the encounter. But here is the subtle clue. Computer simulations of such mergers show that the behavior of those tidal tails depends critically on what you cannot see. If galaxies were just the stars and gas we observe, their collisions would play out one way. But when scientists model these crashes, they find the simulations only match the real, observed shape and speed of the tidal tails when they include massive, extended halos of dark matter around each galaxy. These invisible halos are far larger than the visible galaxy itself, and they interact first. As two galaxies approach, their dark matter halos begin to overlap and tug at each other, long before the stars themselves feel a strong pull. This initial gravitational handshake between the ghosts sets the stage for everything that follows. It dictates the angle of the tails, the speed at which material is ejected, and the ultimate fate of the merger. By meticulously comparing the real mice galaxies to thousands of simulated collisions, astronomers can essentially weigh the dark matter halos. They ask how much invisible mass must be present and where must it be distributed to create the exact celestial sculpture we see today. The answer consistently points to galaxies being embedded in these vast, massive cocoons of dark matter, cocoons that govern their motions and their destinies. This is a quieter proof than the bullet cluster's shocking separation, but it is a proof nonetheless. It tells us the ghost is not just present in the vast emptiness between clusters. It is the hidden foundation of every galaxy, the silent partner in every cosmic dance. But if dark matter is a ghost, what if gravity itself is the trick? For decades, a bold and elegant alternative has challenged the very need for invisible particles. It is called modified Newtonian dynamics, or MND. Its premise is beautifully simple. Perhaps we do not need to invent a whole new, unseen substance to explain the cosmos. Perhaps instead our understanding of gravity is incomplete. Sir Isaac Newton's laws describe the pull of an apple falling to Earth perfectly. Albert Einstein's theory of general relativity masterfully handles the warping of space-time around massive objects. Buttman proposes that on the immense scales of galaxies and clusters, where gravitational accelerations become incredibly faint, the force of gravity behaves differently. It suggests a tiny modification to the equations, a gentle tweak that says gravity becomes slightly stronger in these low acceleration environments than our standard theories predict. This one change, its proponents argued, could explain the flat rotation curves of galaxies and other cosmic mysteries without invoking any dark matter at all. It was a compelling idea, a philosophical razor that sought to explain the universe with what we can see, rather than what we cannot. For a time, it was a serious contender, a brilliant challenge to the emerging dark matter consensus. Then came the bullet cluster. This cosmic collision did not just provide evidence for dark matter. It delivered a direct, observable test that MND, in its purest form, could not easily pass. Remember the clean separation. The map of total mass from gravitational lensing was offset from the map of glowing hot gas. MND could potentially explain one map or the other, but explaining why the two maps are in different places became a profound puzzle. If gravity is simply modified, why would the gravitational pull, the thing that bends the light, be strongest in a place where most of the visible matter is not? To account for this, MND would need to invoke some form of unseen, massive material in the exact location of the lensing map, which, in essence, is just dark matter under a different name. The bullet cluster forced a difficult choice. Either accept that there is indeed something invisible and massive holding the clusters together, or create increasingly complex versions of MND that incorporate hidden mass, defeating the theory's original elegant simplicity. The subsequent analogues, from the baby bullet to the distant El Gordo, each repeated this same stubborn observation, hammering the point home. They showed the separation happening in different orientations at different times in cosmic history and in different levels of collision complexity. For a theory based on a universal modification of gravity, this consistent location-specific evidence was a severe challenge. the cosmic crashes became a clear laboratory. They tested a prediction. The dark matter model predicted a clean separation between interacting and non-interacting components. The pure Mund model did not. The universe, in its violent experiments, kept delivering the same result. This does not mean the quest to understand gravity is over, far from it. But it does mean that the bullet cluster and its family presented a hurdle that the simplest alternative could not leap. They told us that the ghost's fingerprint was not a mirage caused by misreading gravity's rules. It was the signature of a real, physical presence, silently shaping the aftermath of cosmic violence. The ghost's behavior in these cosmic crashes is not just proof of its existence, it is a detailed profile of its personality. Each collision acts like a high-energy physics experiment, ruling out entire categories of what dark matter could be. The clean separation we see, where dark matter sails ahead while normal gas gets stuck, is a devastating result for one idea. It tells us that dark matter cannot be strongly interacting. If its particles bumped into each other or into protons and electrons with any significant frequency, they would have created friction. They would have slowed down, gotten tangled in the mess, and pooled with the hot gas in the center of the wreck. The fact that they did not, time and again, means dark matter is profoundly antisocial. It ignores the normal forces that govern our world, but could it have a subtle social life of its own? Could dark matter particles interact weakly with each other through some unknown dark force? This is where the different collision histories become crucial. The long-lasting separation in the Musket Ball cluster, which has held for billions of years, sets an incredibly tight limit. It tells physicists that if dark matter particles do bump into each other, they do so very, very rarely. Scientists quantify this with a property called the self-interaction cross-section. Think of it as a measure of how big a target each dark matter particle presents to another. The Musket Ball tells us that target must be vanishingly small, far smaller than the cross-section of a proton. This immediately guides the search at particle colliders like the Large Hadron Collider. It tells theorists that if dark matter is made of weakly interacting massive particles, or WIMP, their proposed properties must fit within this incredibly narrow window of almost no self-interaction. Yet the messy, confusing signal from the train wreck cluster, Able 520, initially suggested a tantalizing possibility. That puzzling dark core, seemingly rich in mass but poor in galaxies, looked for a moment like evidence that dark matter might actually stick to itself more than we thought. It hinted at a larger self-interaction cross-section, a ghost that could feel its own kind. This is the beautiful tension of observational science. One object pushes the limits in one direction, forcing us to question our assumptions. The subsequent, more detailed analysis of that cluster, which linked the dark core to faint stars and gas, pulled the parameter back towards zero. Together, these cosmic laboratories are triangulating the truth. They are not giving us a single, simple answer, but a range of possibilities that gets narrower with every new observation. The collisions tell particle physicists where to look, what energies to probe, and what kinds of interactions to disregard. The ghost is defining the rules of its own detection, whispering its constraints across millions of light years, guiding the hands of scientists searching for it in tunnels deep underground. These cosmic collisions are more than snapshots, they are time machines. Each cluster analog, with its unique arrangement of dark matter, galaxies, and gas, is a frozen frame in a billion-year-long film. To understand the full story, astronomers have become cosmic archaeologists. They don't just look at the wreckage, they learn to rewind it. The key lies in the precise positions of the ghost and everything it left behind. Think of it like a detective arriving at a complex car crash. By measuring the final resting places of the vehicles, the skid marks, and the scattered debris, a skilled investigator can reconstruct the speed, the angle of impact, and the sequence of events. Astronomers do the same, but on a galactic scale. The separation between the dark matter clump and the hot gas cloud tells a critical tale. The greater the distance between them, the faster and more head-on the collision likely was. It is a measure of cosmic momentum, the distribution of the galaxies themselves, whether they form a tight swarm or a scattered stream, reveals how much they were slowed by their own gravitational friction during the encounter. But these clues are just the raw evidence. To rewind the tape, scientists feed this evidence into supercomputer simulations. They create a virtual universe inside a machine. They program in the known laws of physics, the behavior of dark matter as a collisionless fluid, and the sticky, dissipative nature of hot gas. Then, they set two virtual clusters on a collision course with an estimated speed and angle and let the simulation run. They watch as the digital clusters merge, the dark matter ghosts through, the gas piles up, and the galaxies scatter. Then they hit pause. They compare their simulated wreckage frame by frame to the actual Hubble and Chandra images of the real cluster. They ask, does our simulation match the shape of the gas cloud? Does it place the dark matter halo in the right spot relative to the galaxies? If it does not, they go back. They adjust the initial conditions, the impact parameter, the relative speeds, and run the simulation again. It is a process of cosmic trial and error, iterating thousands of times until the digital aftermath perfectly mirrors the real one. When the simulation finally snaps into place with reality, something magical happens. The scientists can now press rewind on their simulation and watch the entire history unfold backwards. They can see the two clusters as they were before the crash, separate and whole, sailing through the void on their original trajectories. They can determine the exact angle at which they struck, whether it was a glancing blow or a direct hit. They can clock the collision speed, often millions of miles per hour. Most importantly, they can pin a timeline on the disaster, figuring out not just that it happened, but when the first contact occurred and how long the merger has been underway. This is how a single, chaotic image of a wrecked cluster becomes a dynamic biography. It reveals the history of the cosmic web itself, showing how these gigantic knots of matter have been drawn together again and again by the relentless pull of the ghost's gravity. We are not just mapping dark matter, we are learning to read the stories it writes in the sky. Rewinding these cosmic crashes requires a universe inside a machine. This is where observation meets creation, where the ghost's behavior is tested not in the sky, but in lines of code and rivers of silicon. Cosmologists do not just look at the bullet cluster, they build it from scratch over and over to understand the rules that made it. They start with a blank, digital slate, a virtual cosmos governed by the equations of gravity, fluid dynamics, and particle physics. Into this void, they place two proto-clusters, each a massive halo of dark matter particles, swarming like a digital hive of invisible bees. Nestled within these halos, they sprinkle in virtual galaxies and fill the space with a hot, diffuse gas. Then, with a digital nudge, they set these titans on a collision course. The supercomputer takes over, calculating the gravitational dance of billions of particles, the hydrodynamics of the slamming gas, and the complex feedback from stars and black holes. It is a symphony of physics playing out over millions of simulated years, compressed into weeks or months of real-time calculation. But the simulation is meaningless without a target. This is the indispensable partnership. The target is the real, observed wreckage, the precise lensing map from Hubble, the fiery X-ray glow from Chandra. Scientists run the simulation forward, then freeze the final frame. They compare. Does the simulated dark matter halo end up in the same place relative to the gas as the real one? Do the tidal tails of stars match the elegant arcs in the Hubble image? If the simulation fails, if the ghost behaves wrong, it is not a failure of the universe but of the recipe. So they go back, they tweak the initial conditions, they adjust the ratio of dark matter to normal matter. They experiment with different properties for the ghost itself. What if it is slightly warmer or has a tiny bit of self-interaction? Each new recipe is a new question posed to the cosmos. they run the simulation again, a digital experiment costing thousands of hours of processor time. This iterative process, this relentless cycle of prediction and comparison, is how we validate our entire understanding of cosmology. The bullet cluster and its analogues are not just pictures, they are Rosetta Stones. When a supercomputer, programmed with our standard model of cold, collisionless dark matter and the known laws of physics, produces a virtual wreck that is a near-perfect match for the real one, it is a profound moment. It tells us our map of reality, however strange, is fundamentally correct. The ghost in the machine has finally matched the ghost in the sky. A single ghost is a mystery, but an army of them is a fact. This is the statistical power now being unleashed upon the dark universe. For years, we relied on a handful of spectacular cosmic crashes, each a unique and precious smoking gun. But what if we could survey the entire sky, not for one perfect bullet, but for every single collision, every merger, every cosmic fender bender? This is no longer a hypothetical. Projects like the Dark Energy Survey have already begun this monumental census, scanning vast swaths of the heavens with unprecedented sensitivity. They are not just looking for the dramatic textbook examples. They are collecting every single galaxy cluster they can find, and then, with sophisticated algorithms, sifting through them to identify which are in the act of merging. The result is a growing catalog not of one or two, but of dozens of merging clusters. And with this population, the question changes. It is no longer, does this one cluster show a separation? The question becomes, how many of them do? The answer is transforming the evidence from a series of brilliant anecdotes into an undeniable statistical truth. When you have a few systems, skeptics can argue about peculiar alignments or measurement uncertainties. But when you have 50 or 100, each showing some degree of offset between where the mass is and where the hot gas glows, the argument collapses. The probability that this is all a coordinated trick of perspective or a flaw in our gravity theories approaches zero. The ghost signature is not rare, it is the standard outcome of cosmic violence. This statistical approach is like moving from studying a single, perfect fingerprint to analyzing a database of millions. The pattern becomes the proof. Each new merging cluster added to the catalog is another data point on a graph that screams one conclusion: dark matter is real, it is collisionless, and it is everywhere. The original bullet cluster gave us a clear, beautiful signal. Now, these surveys are giving us the signal-to-noise ratio, and the signal is deafening. The case is no longer built on a few spectacular crime scenes, but on the cold, hard math of prevalence. We are witnessing the transition from discovery to demography, from proving the ghost exists to understanding how it lives and moves as a population across the cosmos. This shift is crucial because it removes the last refuge of alternative explanations. A modified law of gravity must now explain not just one clean separation, but a whole zoo of them, each with different collision speeds, angles, and stages of completion. The statistical weight is becoming insurmountable, and this is just the beginning. The future belongs to the Vera C. Rubin Observatory and its legacy survey of space and time, or LSST. This monumental project will not just find dozens of merging clusters, it will find thousands. It will map the sky in such detail and over such a vast volume that we will see the entire life cycle of cluster mergers, from the first gravitational whispers to the final relaxed giants. We will have a statistical sample so large we can categorize mergers by type, by age, by mass. We will see if the ghost behaves slightly differently in younger, more turbulent collisions versus older, settled ones. This ocean of data will let us measure the properties of dark matter with a precision we can barely imagine today, tightening the constraints on its self-interaction cross-section to a vanishingly small number, or perhaps revealing a subtle deviation that points to a richer, more complex dark sector. The journey from the single, shocking image of the bullet cluster to the coming flood of thousands, is the journey from a brilliant hypothesis to an established pillar of modern cosmology. We are not just collecting evidence anymore, we are mapping the habitat of the invisible. The statistical census of cosmic crashes is closing the book on simple alternatives, but it may be opening a far stranger one. With thousands of mergers to study, we are no longer just confirming the ghost exists. We are looking for the faintest tremor in its step, a hint that the dark sector might have its own hidden richness. The perfect, clean separation predicted by the simplest dark matter model is a powerful guide, but nature rarely deals in perfections. What if the ghost, while overwhelmingly antisocial, has a whisper of a social life? This is where the most speculative and thrilling ideas in physics emerge from the data, concepts like dark photons. Think of the forces in our visible world. Light carried by particles called photons is the messenger of the electromagnetic force. It allows charged particles to push and pull. A dark photon would be a hypothetical messenger particle for a dark force, a shadow version of light that operates only within the dark sector. It would be a conduit allowing dark matter particles to interact with each other, not through the strong, sticky collisions of normal matter, but through a faint, unseen influence. How would we ever detect such a thing? The answer lies in the exquisite details of those merger maps. In a universe with dark forces, the behavior of dark matter during a collision might show subtle deviations. Instead of two clumps of dark matter passing through each other completely unimpeded, a dark photon-mediated force could cause a slight drag, a barely perceptible slowing. This could manifest as a smaller offset between the dark matter and the galaxies than the pure collisionless model predicts, or it could cause the dark matter halo itself to puff up or distort slightly after the crash. The key word is slight. We are not talking about dark matter getting stuck like the gas, but about a minuscule hesitation in its ghostly stride. This is why the coming flood of data from observatories like the Vera C. Rubin Observatory is so revolutionary. To see these whispers, we need immense statistical power. We need to compare hundreds of mergers, categorize them by their collision speed and angle, and look for systematic, tiny discrepancies in how the dark matter behaves. It is like trying to hear a single soft note in a roaring symphony. You need to record the symphony 1,000 times and average out the noise to find the consistent, hidden melody. These wild theories are not flights of fancy, they are direct responses to the precision of our cosmic maps. The bullet cluster gave us a bold, black and white answer. The next generation of analogues may reveal a spectrum of subtle grays, hints of a hidden complexity in the dark universe that is only now coming into focus. The ghost's silent dance may soon have a soundtrack. Beyond the warped light and the fiery gas, there is another messenger from these cosmic collisions, one that shakes the very fabric of space-time itself. We are on the cusp of hearing the universe's most violent mergers through gravitational waves. These are not ripples in water or air, but literal waves in the fabric of reality, first predicted by Einstein and now confirmed by detectors like LIGO from colliding stellar mass black holes. But the future holds a far grander listener. The Laser Interferometer Space Antenna, or LISA, is a next-generation observatory that will not be built on Earth but in the quiet of space. It will consist of 3 spacecraft flying in a perfect triangle millions of miles apart, connected by laser beams. Its mission is to detect the low-frequency hum of the universe's heaviest dancers, the supermassive black holes that sit at the center of nearly every large galaxy. When 2 galaxy clusters collide, their central supermassive black holes are brought together in a final, catastrophic embrace. As they spiral inward over millions of years, they churn the space around them, sending out powerful, rhythmic gravitational waves. LISA will be tuned to hear this specific cosmic frequency. Imagine witnessing a car crash in complete silence, and then one day, someone hands you a device that lets you hear the precise moment of impact, the screech of metal, and the deep thud of collision. That is what LISA will provide for these cluster mergers. It will give us a precise timestamp and a measurement of the black hole's masses and spins, all from the tone and rhythm of the space-time ripples they produce. Now combine that soundtrack with the silent movie we already have. We will have the gravitational wave signal telling us the exact dynamics of the central black holes. We will have the Hubble map showing us where the dark matter ghost ended up, and we will have the Chandra image revealing where the normal matter gas was left behind. This is the ultimate multi-messenger portrait of cosmic violence. Each messenger, light, X-rays, gravitational distortion, and space-time ripples, tells a different part of the same story. By synchronizing them, we can ask profound new questions. Does the dark matter distribution affect how the black holes spiral together? Can the gravitational wave signal tell us if the black holes were kicked off center by the slingshot effect of the ghost's gravity? This fusion of senses will transform our understanding from a series of snapshots into a full, immersive experience with sound, sight, and depth. We will not just be mapping the ghost, we will be listening to the echoes of its most powerful gravitational deeds. The silent symphony of collisions now has a new conductor, one with vision that pierces the cosmic dust. The James Webb Space Telescope is not just another observatory, it is a revolution in how we see the dark universe. Its primary superpower is infrared vision. While telescopes like Hubble see the universe in visible and ultraviolet light, and Chandra sees the high-energy X-rays, Webb sees the longer, redder wavelengths of infrared. This is the key that unlocks a hidden layer of the merger mystery. In the chaotic wreckage of colliding clusters, vast clouds of dust and gas often obscure the true distribution of stars. Hubble sees the brilliant cores of galaxies, but it can miss the faint, diffuse starlight that gets stripped away during the collision, the very stars that might hold clues to the dark matter's grip. Webb's infrared eyes cut through that obscuring fog. Dust that blocks visible light is transparent to Webb's longer wavelengths. This allows it to map, for the first time with stunning clarity, the total stellar mass distribution in these titanic crashes. It sees not just the bright galaxy cores, but the faint sea of stars torn loose into tidal tails and intracluster light, the ghostly glow of stars floating free in the darkness between galaxies. Why is this a game changer? Until now, we had two primary maps, the dark matter from gravitational lensing and the hot gas from X-rays, but there was always a lingering uncertainty, a degeneracy in our models. When we saw a clump of mass from lensing, we had to infer how much of that mass might be tied up in faint stars versus pure dark matter. Webb breaks that degeneracy by giving us the third, independent map, the map of stars. Now we can perform a cosmic accounting of staggering precision. We can take the total mass map from lensing, subtract the map of stellar mass from Webb, and then subtract the map of hot gas mass from Chandra. What remains with minimal guesswork is the pure dark matter distribution. This is like having a detailed inventory of a shipwreck, finally separating the weight of the metal hull, the cargo, and the seawater to find the exact mass of the hidden treasure buried within. For distant analogues like El Gordo, seen when the universe was young, this precision is transformative. Webb can measure the stellar mass in those ancient collisions with a fidelity we have never had before. This lets us ask profound new questions. Did dark matter and stars separate in the same way in the early universe as they do today? Or were the ghosts of the young cosmos behaving differently, perhaps clumpier or more turbulent? By adding this crucial third data point, Webb is not just confirming the dark matter story, it is reading the fine print, revealing the subtle clauses and conditions in the contract that shaped our cosmos. Each distant cluster becomes a cleaner, sharper laboratory, and the ghost's profile becomes more detailed than ever. Yet even with this growing arsenal of proof, the ghost still throws us curveballs. For every clean, textbook separation, there remains a puzzling outlier that refuses to fit the mold perfectly. The initial shock of the train wreck cluster, Able 520, was a prime example. That dark core, seemingly rich in mass but devoid of bright galaxies, created years of intense debate. Was it evidence of dark matter interacting with itself? Or was it a sign our maps were missing something? Science thrives on these tensions, on the data point that does not neatly fit the graph. It is the anomaly that forces us to look harder, think deeper, and question our own assumptions. While the consensus around cold, collisionless dark matter is stronger than ever, thanks to the statistical weight of dozens of mergers, these lingering puzzles are not failures. They are the engines of discovery. They remind us that our models are approximations of a far more complex reality. Perhaps the simplest model is mostly right, but needs a tiny adjustment, a faint whisper of self-interaction or a new particle property. Or perhaps the anomaly is not in the ghost itself, but in our ability to observe it. Could complex projection effects, where multiple structures along our line of sight create an illusion of a single, weird core, explain some of these oddities? The process of wrestling with a system like Able 520 led to better observational techniques and more sophisticated simulation codes. It forced astronomers to account for faint starlight and dim gas they might have previously overlooked. This is how science self-corrects and marches forward. The overall case for dark matter does not rest on every single cluster being perfect. It rests on the overwhelming, repeatable pattern. But the exceptions are where the next breakthrough might be hiding. They are the cracks in the door, the slight tremors that hint at a richer, stranger dark sector than we ever imagined. Our map of the invisible is detailed, but it is not yet complete, and the remaining blank spaces are the most exciting places to look. Mapping the ghost's behavior does more than solve a cosmic mystery. It tells us the ultimate fate of everything. Every precise measurement from these colliding clusters, every map of its invisible mass, feeds directly into cosmology's greatest question: how will the universe end? The answer hinges on a silent, universe-spanning tug-of-war, and dark matter is one of the two titans on the rope. Its opponent is an even more enigmatic force: dark energy. Think of the cosmos as a vast, stretching canvas. Dark matter, with its relentless gravitational pull, acts like an anchor. It tries to gather matter together, to slow down the expansion of space that began with the Big Bang. Its gravity is the cosmic glue, working over billions of years to build the web of clusters and filaments we see. Dark energy, on the other hand, is the anti-gravity. It is a repulsive force woven into the fabric of space itself, causing the expansion of the universe to accelerate, pushing galaxies apart from one another faster and faster. The entire future history of the cosmos depends on which of these two invisible giants wins. Will dark matter's gravity eventually halt and reverse the expansion, leading to a catastrophic big crunch? Or will dark energy's repulsion dominate forever, leading to an endless, cold, and lonely expansion where galaxies fade from view? The critical parameter that decides this is the total amount and the clumpiness of dark matter in the universe. And this is where our cosmic crash sites become the most important scales we have. By studying thousands of merging clusters, we are not just proving dark matter exists, we are weighing it with phenomenal precision. The gravitational lensing maps from these collisions give us a direct measure of how much dark matter is in a given volume of space. But even more crucially, they tell us how that dark matter is distributed, its clumpiness. This property, which scientists call the matter-power spectrum, is a fingerprint of the early universe. The way dark matter clumps together today, forming these massive halos around clusters, tells us about the initial conditions after the Big Bang and the nature of the dark matter particle itself. Was it cold and slow-moving, allowing it to clump easily from the start? Or was it warmer, suppressing the formation of small structures? The bullet cluster and its analogues, by confirming the cold, collisionless model, lock in a specific prediction for how clumpy the universe should be on large scales. This predicted clumpiness is then compared to the actual observed expansion rate of the universe driven by dark energy. It is a balancing act of cosmic accounting. If we overestimate the amount of clumpy dark matter pulling things together, our models cannot match the observed accelerated expansion. If we underestimate it, the universe will be expanding differently than we see. The precise measurements from cluster collisions provide the anchor for one side of the equation. They tell us with growing certainty the strength of the gravitational hand trying to pull the cosmos back together. Only with that number locked down can we truly measure the strength of the dark energy hand pushing it apart. Every new analog, every more detailed map from Webb or gravitational lensing survey tightens these constraints. They are giving us the census of the invisible mass that governs the large-scale structure of reality. So when you look at that ethereal blue haze in a cluster map, you are not just seeing proof of a ghost, you are looking at one half of the ledger that will determine whether the universe ends in fire, ice, or something beyond our current imagination. The fate of all existence is written in the silent aftermath of these cosmic crashes. The cosmic wreckage has given us a detailed profile of the ghost, but the final identification must happen here on Earth. The fingerprints we have collected from deep space, the precise measurements of how dark matter behaves and what it does not do, are now the most wanted posters in modern physics. They are not just curiosities for astronomers, they are essential blueprints for engineers and experimentalists building machines to catch the ghost in the act. Every property we constrain in the heavens tells a particle physicist exactly where to aim their most powerful instruments. Take the most critical clue from the bullet cluster and its analogues, the profound lack of interaction. The fact that dark matter ghosts through those collisions with such ease tells us its particles must be incredibly shy. They must have an extremely low cross-section, a tiny probability of bumping into a proton or neutron in the normal world. This single astrophysical fact rules out vast swaths of potential candidates. It tells scientists at the Large Hadron Collider that if dark matter particles are being created in their high-energy proton collisions, those particles will almost certainly not leave a direct, messy track in the detectors. They will be silent escape artists carrying away energy and momentum without a trace. So, the experiments are designed to look for that exact signature, an imbalance, a missing piece of the energy puzzle that hints at something invisible fleeing the scene. The cosmic data says, do not look for a splash, look for a whisper. Similarly, the mass range for what dark matter could be is heavily guided by the sky. The way dark matter clumps to form the halos around galaxies and clusters, a property measured meticulously through gravitational lensing and simulations, points strongly toward it being cold, meaning the particles were moving slowly in the early universe. This favors candidates with substantial mass, not featherweight particles zipping around at near light speed. This astrophysical guidance is why a leading candidate for decades has been the WIMP, the weakly interacting massive particle. Its proposed properties of having mass and interacting only through the weak nuclear force and gravity fit beautifully with the cosmic evidence. It is the hypothetical particle that matches the ghost's profile from the clusters. This is why teams have built exquisitely sensitive experiments deep underground, in old mines and beneath mountains. Places like the Sanford Underground Research Facility in South Dakota house detectors like LUX Zeppelin, a tank of ultra-pure liquid xenon shielded from cosmic rays by a mile of rock. Their entire design is based on the astrophysical prediction. They are waiting in utter stillness for the once-in-a-universe chance that a WIMP, with just the right mass and interaction strength implied by the cosmos, will drift through their chamber and nudge a single xenon nucleus, producing a faint flash of light and a trickle of charge. The expected signal is so incredibly rare because the sky told us it would be. Every time a new cluster merger refines the limits on dark matter's self-interaction, it directly translates to the engineers tuning their detectors. If the cosmic data says the ghost's self-interaction cross-section must be smaller than a certain value, the experiments can rule out any theoretical model that predicts a larger one. It is a continuous dialogue. The heavens provide the constraints and the labs test the theories that fit within them. We are not searching blindly in the dark. We are following a map drawn by the most violent events in the universe, using colliders to attempt to create the ghost, and underground vaults to try and catch it as it passes through our world. The silent aftermath of collisions millions of light years away is shouting instructions to our greatest machines. We have built a detailed atlas of a ghost. This is not hyperbole, it is the literal truth of modern cosmology. We have charted the distribution, measured the mass, and even inferred the fundamental personality of a substance that gives us nothing, no light, no radiation, no direct signal of any kind. Its presence is known only by the empty space it bends and the wreckage it leaves behind. This achievement stands as one of the most profound triumphs of the human intellect, a masterclass in indirect reasoning. For most of human history, what we could not see, we could not know. The world was limited to the horizon of our senses. Then came the scientific method, a toolkit for listening to the whispers of the universe. We learned to ask nature subtle questions and design experiments to hear its faint replies. The mapping of dark matter is the ultimate expression of this process. We did not stumble upon it glowing in a telescope. We predicted its necessity from the misbehaving orbits of stars. We designed a cosmic experiment, waiting for the universe to provide the violent collisions. We built telescopes to see in X-rays and to measure the delicate warping of space. And then we assembled the clues, a gravitational fingerprint here, a displaced gas cloud there, into a coherent portrait of the invisible. It is detective work on a galactic scale, where the crime scene is 1,000,000 light-years wide, and the suspect leaves no physical trace, only a gravitational shadow. This is how we know the world. We once believed air was empty space until careful experiments showed it had weight and substance. We thought diseases were caused by bad air or divine wrath until we built microscopes and saw the bustling world of germs. We were convinced matter was solid and continuous until we devised ways to split the atom and peer into a vibrating, mostly empty quantum realm. Each of these leaps required the same fundamental shift, trusting the evidence of indirect effects over the illusion of direct perception. Dark matter is the latest and grandest chapter in this story. We are mapping the architecture of reality not by what shines, but by what pulls. Every ethereal blue haze in those cluster maps is a testament to our species' stubborn refusal to accept the limits of our eyes. It is a map drawn not with light, but with logic, patience, and an unwavering faith that the universe, even in its silence, is always speaking to those who know how to listen. The ghost's signature is hiding in plain sight, waiting for anyone to learn its visual language. You do not need a doctorate in astrophysics to spot the cosmic wreckage that proves dark matter's reality. You just need to know what to look for. The next time you are browsing through a stunning public release from the Hubble Space Telescope or the James Webb Space Telescope, pause on any image of a galaxy cluster. Your first instinct might be to marvel at the brilliant pinpoints of light, the galaxies themselves. But the real story is written in the spaces between them and in the subtle distortions of the background sky. Start by hunting for strange, thin arcs of bluish light, often curved like a smile or stretched into long, faint lines. These are not part of the cluster. They are gravitational lensing arcs, the distorted images of galaxies billions of light years behind the cluster. Their very presence and their curved shape is a direct billboard announcing massive invisible gravity here. If you see multiple arcs or a so-called Einstein ring, you are looking at one of the strongest gravitational lenses known, a place where the dark matter ghost is bending space like a heavy lens. Next, look for the overall shape of the cluster's galaxies. Are they neatly gathered in a round, smooth ball that suggests a relaxed, settled system? But if the galaxies seem strewn out in a line, or if you see two distinct clumps of them with a bridge or a tail of stars stretching between, you are likely witnessing a merger in progress. It is the cosmic equivalent of seeing two swarms of bees that have just passed through each other, still trailing their companions. Now, find the counterpart image from the Chandra X-ray Observatory. These are often presented in false color, usually deep reds or purples. Look for a huge, diffuse cloud glowing in that color, enveloping the galaxies. In a relaxed cluster, this hot gas cloud will be symmetrical, centered on the main galaxy swarm. In a merging cluster, the story changes dramatically. The gas cloud will look lopsided, distorted, or even split into two distinct blobs. Most tellingly, it will often be displaced, sitting off to one side of the galaxy swarms. That separation, visible even to an untrained eye when comparing the optical and X-ray images side by side, is the ghost's clearest calling card. It is the evidence that the sticky normal matter got left behind. This is not just an academic exercise. You can join the hunt yourself. Platforms like Zooniverse host citizen science projects where volunteers help professional astronomers scan through thousands of telescope images to identify gravitational lenses, classify galaxy shapes, and even flag potential cluster mergers for further study. Your eyes, looking for those telltale arcs and asymmetries, could help find the next great dark matter analog, the next cosmic crash that adds another piece to the map of the invisible. The universe has written its proof across the sky, and now you know how to start reading it. Our current maps of the ghost are detailed, but they are still just sketches. The true census of the invisible universe is about to begin. A new generation of cosmic observatories, now being built or poised to launch, will not just find more bullet cluster analogues, they will flood us with them, transforming our statistical handful into a vast cosmic library. Leading this charge is the Vera C. Rubin Observatory in Chile. Its mission is nothing less than a 10-year movie of the entire southern sky. Night after night, its enormous mirror and giant camera will capture the heavens, not to take pretty pictures, but to detect change. It will find moving asteroids, exploding stars, and most importantly for our hunt, the subtle warping of light from billions of distant galaxies. This relentless survey will identify not dozens, but thousands of galaxy clusters in the act of merging. For the first time, we will have a population so large we can sort them by age, collision speed, and geometry. We will see the ghost's behavior in every possible scenario, building an unshakable statistical profile of its collisionless nature. But Rubin is just the beginning. The European Space Agency's Euclid telescope is already in space, its gaze fixed on the dark universe. While Rubin scans from the ground, Euclid observes from the pristine blackness of orbit, measuring the shapes of over 1 billion galaxies to create the most precise map of cosmic structure ever made. It will trace the invisible scaffolding of dark matter across 10 billion years of cosmic history, watching how the ghost's web grew from the early universe to today. Then comes Athena, the advanced telescope for high-energy astrophysics. This future X-ray observatory will be like Chandra with superhuman vision. It will see the hot gas in merging clusters with such stunning clarity and sensitivity that we can measure its temperature, motion, and composition in exquisite detail. This will let us reconstruct the violence of each collision with forensic precision, telling us exactly how much momentum the ghost carried away. And looking further ahead, the Nancy Grace Roman Space Telescope will combine Hubble's sharp vision with a field of view 100 times wider. It will perform wide-area surveys in infrared light, piercing cosmic dust to map the stellar mass in and around thousands of merging clusters, completing the accounting that Webb began. Together, this fleet of instruments will operate in concert. Rubin and Euclid will find the mergers and map the dark matter. Athena will study the shocked, glowing gas. Roman will tally the stars. We will have a multi-wavelength, multi-messenger portrait of thousands of cosmic crashes, each a complete data set. This ocean of information will allow us to ask questions we can barely formulate today. Does dark matter behave exactly the same in collisions that happened when the universe was a quarter of its current age? Do we see any systematic, tiny deviations from perfect collisionless behavior that could hint at those dark forces or dark photons? Most profoundly, this data may hold clues to dark matter's primordial origin, the moment it was forged in the first instance after the Big Bang. The specific way dark matter clumps together, a pattern imprinted in those early moments, is frozen into the large-scale structure we see today. By comparing the ghost's distribution in ancient mergers versus recent ones, we can test theories about what the dark matter particle actually is. Was it created in the searing heat of the Big Bang, a relic from a more symmetric time? Or did it condense later as the universe cooled? The patterns in thousands of collisions will act as a cosmic fossil record, a diary of the dark sector's birth. We are on the verge of moving from proving the ghost exists to reading its autobiography, written in the silent aftermath of countless cosmic wrecks across all of time. That single, shocking image of the bullet cluster was just the opening sentence in a much longer story. What began as a solitary smoking gun has grown into an entire arsenal of evidence, a gallery of cosmic collisions, each repeating the same impossible tale. We have witnessed the clean separation in the baby bullet, the enduring proof in the ancient musket ball, and the chaotic stress test of the train wreck cluster. We have seen the ghost building titans like El Gordo in the young cosmos and being filtered from the normal matter in the tangled wreckage of Pandora's box. This is no longer a hypothesis waiting for confirmation. Dark matter is an observed architectural component of the universe, as real as the stars, even if it remains unseen. Its gravitational fingerprint is now mapped across dozens of systems, its collisionless behavior confirmed by statistics, and its properties constrained by the violent physics of merging giants. The ghost has been profiled. We know how it moves, how it clumps, and how it dominates the gravity that sculpts everything we see. Yet for all we have mapped, the central mystery remains wonderfully intact. We still do not know what it is. That question now passes from the realm of astronomy to the frontier of particle physics, guided by the precise blueprint these cosmic crashes have provided. So as we look back at this journey from a single bullet to a universe of analogues, the feeling is not one of an ending but of a threshold crossed. We have moved from asking if the ghost is there to learning how it lives. Which of these cosmic collisions left the deepest impression on you? Was it the elegant simplicity of the original bullet or the tangled history of Pandora? And as you look at those maps of blue gravity hanging in the darkness, what do you imagine the ghost might be?